The first two problems address two situations. One situation ultimately leads to analysis of the field of an infinite line current at a point somewhere that's not on the current carrier. The other, the field of a current running around a loop at a point on the central axis perpendicular to the loop. So we'll look at both of these separately. Now we do have the fact that the magnetic field is K prime times I dl cross R over R cubed. Now I prefer to write that as I wrote it here with R over the magnitude of R, the R vector over the magnitude of R, to emphasize this is a unit vector that's being crossed with the vector indicating the current distance product. Okay, and then the inverse square here. But of course, this R can go with this R to give us an R cubed. So sometimes we'll use this, but usually I like to write it like this, again, to emphasize the unit vector and the inverse square. Okay, well, what we do is first, the question asks us to calculate the field at the point x0z due to a delta x increment, and it's a vector increment, it's got a direction, a delta x vector increment on the x-axis, where that increment contains a sample point x star, and there's a current I flowing through this increment. The key to calculating this, we have a symbol for I, we have a symbol for delta x. All we need is to write R in terms of the given sample point, the sample point x star, and the point x0z. So once we have R, we can find its magnitude and we can substitute and get our expression for the magnetic field due to the current running through this increment. Now this is an approximation. We assume the increment is small enough that the R vector from one point in the increment to our field point is very nearly the same as the R vector from any other point from the increment, any other point in the increment to the field point. Okay, so anticipating that we're eventually going to sum these contributions up over a long charge or current distribution, I'm going to call this contribution delta B. So delta B will be the contribution of the current in this increment to the charge, to the magnetic field at this point. Okay, well, our R vector goes from sample point to here. Sample point is at point x star on the x-axis. This is a point x02, so we very easily get the R vector. The x displacement from here to here is x minus x star, this coordinate minus this coordinate, and that's in the I direction. And then we have zk. We go z units in the k direction. So here's our R vector, and now we just substitute all that in. Excuse me. We have our I delta x, which is now going to be positive. So we have I delta x times the I vector. That's the the delta x vector could be taken as delta x times the I vector. The current I then is multiplied by that to give us our I dl. And we cross that with the R vector that we have up here. And then we divide here by the cube of the magnitude of the R vector. Magnitude of the R vector is by the Pythagorean theorem, just the square root of x minus x star squared plus z squared. If we cube that, we get the 3/2 power of x minus x star squared plus z squared. And then we get the result. Okay. I vector crossed with the I vector gives us 0. I vector crossed with the k vector gives us negative j. So we have negative j from the cross product of the I with the k vector. And also from that cross product, we get z. The x minus x star in the numerator being a multiple of I, which crossed with this I gives us 0, doesn't appear in our expression. So our numerator is going to be, well, we have negative k prime j times I delta x and z. The denominator is just what it was before. So there's our contribution. Now, in a few minutes, we'll get to the third problem. And when we get there, we'll see that this leads us very easily to an integral. And we'll write down the integral. Then I'll go ahead and do the integral in a supplementary video. I didn't do the integral in class. Okay, now go to the loop. In the case of the loop, and let me move this over just a little bit. Okay, lighting stays a little bit better. Okay, the situation is we have a loop in the xy plane of radius a. And we have an increment, and we have a current running counterclockwise around the loop. Excuse me. Now, really hasn't been a bad allergy season, but something today's bothering me. Okay, so again, loop of radius a in the xy plane, current I running counterclockwise around the loop, and we're going to define our increment of that current in terms of an angle delta theta and a position theta star, sample position theta star within this delta theta increment. We get a delta S vector parallel to this increment. Now, of course, this increment is an arc, but if we have a small delta theta, that arc is very close to a straight line, so we're going to approximate that arc with our delta S. So our sample angle is theta star. What's our sample point in this increment? Well, the sample point is simply going to be the point that we get at angle theta star relative to the positive x-axis running in the counterclockwise direction. It should be clear that that point is a times the cosine of theta star, a times the sine of theta star. Now, I've also wrote it down here. The sample point in the delta S increment can be represented in vector form by a times cosine theta star I plus sine theta star j. And that's just very fundamental, most fundamental thing that you should know about vectors. So hopefully that's not a problem. Okay, so in vector form or in coordinate form, there's our sample point. Our delta S vector, first of all, it has magnitude a delta S, because an arc that subtends angle delta theta will have length a delta theta. So that's going to be the length of the arc, and the direction of the arc is going to be at 90 degrees with the direction of the theta star line, if you wish, and that direction is going to be minus theta star I plus cosine of theta star j. You can confirm that that's perpendicular to the direction of this vector. Yeah, dot product being 0, and in many ways you can validate that this is the correct vector. So here's our delta S vector. Our R vector is just negative a cosine theta star I minus a sine theta star j plus zk. Why is that? Well, our R vector goes from our sample point here, which is a cosine theta star, a sine theta star in the xy plane, and I probably should have put comma 0 here, because there's a z coordinate, because we're in 3 dimensions. Okay, from this point, which is our sample point on the increment, to the point 0, 0, z, we simply subtract these coordinates from these coordinates, and this is what we get. So now we're going to be able to put all this information into this formula, this relationship that gives us the magnetic field at our field point.